Good morning, ma'am, and my dear friends. Thank you for being here today. My name is Divya, and my roll number is 5407. Today, I am going to give a short presentation on regularity and normality of compact hausdorff space. Let us have a look at the topic which I am going to discuss with you. First, introduction. Second, theorem. After that, we will talk about examples and then we will move to the properties. Then, links and references are given. Firstly, I want to tell you about Felix Hausdorff, who is well known for Hausdorff measure and Hausdorff dimension. The credit for the compact Hausdorff space also goes to him. He was a German mathematician who is considered to be one of the founders of modern topology. He also contributed significantly to the set theory, descriptive set theory, measure theory, function theory, and functional analysis. Let us look at the introduction. In topology and related branch of mathematics, a Hausdorff space, which is also known as separated space or T2 space, is a topological space where for any two disjoint points there exists neighborhood of each which are disjoint from each other. Hausdorff space are named after Felix Hausdorff, one of the founder of topology, which I had already said. Hausdorff's original definition of topological space in 1914 included the Hausdorff condition as an axiom. Hausdorff condition is sometimes called T2. Now, I would like you to focus on the theorems. Here is the first theorem in which we are going to prove that every compact Hausdorff space is regular and hence T3. Firstly, a topological space is said to be regular if and only if it satisfies an axiom. That is, if f is a closed subset of x and x is a point of x not in f, then there exist two disjoint open set, one containing f and other containing x. The question arises how to prove the theorem. So now concentrated on the proof of the theorem. Let Xt be a compact Hausdorff space. Let X belongs to the compact Hausdorff space and F be the closed subset of X not containing X. Let Y belongs to F, then Y and X are disjoint. Since X is a T2 space, there exist two disjoint open sets gy and hy such that x belongs to gy and y belongs to hy. This collection hy such that y belongs to f form an open covering of f. Also, f being a closed subset of a compact space is compact. Now, the covering hy such that y belongs to f must reduce to the finite subcovering, say hy I, and such that y is from 1 to n. And the covering must reduce to the finite subcovering. This is the property of the compact Hausdorff space. Let h is equal to union of I is from 1 to n hyi. Let gyi such that y is from 1 to n be a corresponding family of open set containing x. Write G is equals to intersection I is from 1 to n gyi. Thus we have find two disjoint open sets G and H such that x belongs to G and F is the subset of H. Hence, Xt is a regular space. Also, every T2 space is T1 space. Therefore, T1 space is T3 space. Let us come to the next theorem, in which we have to prove that a compact Hausdorff space is normal and hence T4. A topological space is said to be normal space if and only if it satisfies the axiom, that is, if F1 and F2 are two disjoint closed subsets of X, then there exists two disjoint open sets, one containing F1 and other containing F2. The proof of the theorem is as follows. Let F and F star be the two disjoint closed subsets of X of a compact Hausdorff space X. Then F and F star are also compact, since closed subsets of a compact space are also compact. Let X belongs to F and X star belongs to F star, then X is disjoint from X star. By the Hausdorff property of X, there exist two disjoint open sets, Gx X star and G star X X star, such that X belongs to G X X star and X star belongs to G star X X star. Now, for each fixed X belongs to F, the collection G star X X star such that X belongs to F star form an open covering of F star. Since F star is a compact, this covering must reduce to a finite subcovering, say G star X Xi star and I from 1 to n. Let G star X is equals to union i's from 1 to n, G star X Xi star, and G is equals to intersection i's from 1 to n, G X Xi star. Then Gx and G star X are disjoint open sets containing X and F star respectively. The collection Gx such that X belongs to F form an open covering of F. Since F is a compact, there must be some finite subcovering, say Gxi, I is from 1 to n of this covering. Let G is equals to union of i's from 1 to m, Gxi, and G star is equals to intersection i's from 1 to m, G star Xi. Then G and G star are disjoint open sets such that F is the subset of G and F star is the subset of G star. It proves that X is a normal space. That's all I have to say about the theorems and their proofs. Now I would like you to move on the examples related to the theorem. Almost all the spaces encountered in the analysis are Hausdorff. Most importantly, the real number and the metric spaces are Hausdorff space. In fact, many spaces used in analysis such as topological group and the topological manifolds have Hausdorff condition explicitly stated in their definition. A simple example of a topology that is T1 but is not a Hausdorff is a cofinite topology defined on an infinite set. After this, I would like to turn to the properties. Subspaces and the product of Hausdorff space are Hausdorff, but the quotient space of the Hausdorff space need not be Hausdorff. Compact spaces are T1, meaning that all the singleton sets are closed. Another property of the compact Hausdorff space is that compact sets are always closed. In the Hausdorff space, every pair of disjoint compact set can also be separated by neighborhoods. In other words, there is a neighborhood of one set and the neighborhood of other, such that the two neighborhoods are disjoint. This is an example of the general rule that compact set often behave like points. Here are some links related to the theorem. These links will help you to know well about my topic. But if you still wish to study about the compact Hausdorff space more clearly, then I have provided you with some YouTube links. I hope that these online links will help you. This brings me to the end of my presentation. Here you are also being told about some references related to the theorem. Thank you for listening and for paying attention. I will be glad to answer any question you might have.